second day of the Beyond the Standard Model conference. I will be introducing our second speaker of the day by Dr. Carmargo-Molina from Imperial. He will be talking about probing the intersection of cosmology and particle physics. A little bit about Dr. Carmargo. His research is really based in finding new approaches to beyond standard model physics, and also new novel approaches in testing these models. So thank you for being here, and I will happy to introduce Dr. Carmargo.
Perfect. Thank you very much for the introduction. I'm very happy to be here, and I'm very excited to talk to you about these kind of things that I tend to think about sometimes. So first, do you see my screen properly? I'm sharing it. Should be able to see the slides. Okay. And you hear me well as well. Okay. So as mentioned, and as clear from the title, I'm going to try to give you a little bit of an overview first about why, in my opinion, it makes sense to think about beyond the standard models. And it has an S at the end because it's thinking beyond both the standard model of particle physics, but also the standard model of cosmology. And even though this is a super broad topic, I'm going to have to focus on what I think are a couple of examples of where the most interesting prospects for discoveries or for testing and probing the thing will be in the next years. So before we go on into that, I wanted to give a little bit of motivation about why this makes sense to think about. This is a question that it's first not new. Like in my reading about history, preparing for this talk and trying to give an overview of the subject, I actually found a very interesting document, a letter written already in 1983, where a lot of the ideas that people are talking about today that sound or might sound new were already there. And this is because connecting the very small things and the very large things has been a very, very appealing goal for physicists for a long time. This has many reasons. The most powerful one, in my opinion, is because it's also dealing with this fundamental big question of how do we couple gravity and the particle world. But also, since people started thinking about unifying the forces and taking grand unified theories, this has been a very interesting question, because then you're taking particle physics models and extrapolating them to very high energies, to the point where you cannot just say gravity is not important anymore. You have to think about these things. And in fact, even though this might be kind of like a new field, or I think people might feel like that, we already have learned some stuff from cosmology within particle physics. And primarily, I come from the particle physics world, and slowly but surely have been thinking more about cosmology. And one of the things that is interesting is to think that before we knew there were three neutrinos from accelerator physics, from measuring the set physics properties at LEP, we knew that there were three neutrinos, more or less, from cosmology. And even today, still we only know that there's an upper bound on the neutrino masses when we use cosmological observations, and the fact that it's almost massless. So you take into account that, and it pops out that you can actually derive, the details are perhaps beyond the scope of this talk, but you get an upper bound of how massive neutrinos can be. And this is still only coming from cosmology. Also, in the other way, nuclear physics has been fundamental for understanding like the abundances of different elements, star formation, and all of that stuff. So there's already kind of like a cross-pollination. But I want to just focus this talk on talking not about everything that we've known so far, which is incredibly humbling and interesting and powerful, but I want to just focus on what we don't know. So I just hope the message of this talk is not taken as like we don't know anything. I just want to make the point that I'm going to focus explicitly on those things that have the biggest question marks, because I think that's at least what excites me about physics, knowing what is left to discover more than what it is. But we have to start with what we know. So I'm going to try to do a tour de force through both standard models in 2 minutes. Let's see if that works. Hopefully you've already gotten pretty good background on these things already in the previous talks. So the standard model of particle physics, you can think of it, as you probably already know, as kind of like a table of elements of all the particles that are there. So essentially what we have is just a set of, a complete model of a list of all the particles that we have, together with not only fermions, but also the interactions that are governing how they behave and the physics that happens at that scale. What's interesting to note, besides all the details that we have quarks, we have leptons, and so on, is the fact that we have 3 copies. We have 3 generations that, excluding the mass, which is very different, excluding that only fact, they are identical. And this is striking because the difference between the mass of the top quark and the up quark has a factor of 80,000. And that's interesting. It's interesting. You might argue that, well, that's the way it is. But to any curious mind, it pops the question, why is it that way? Why are they identical, but also so different in just one thing? And they all interact in a very specific way. You have the weak force, the strong force, and as you can see here, they are connected and interact with each other in these different ways. And this is governed by the symmetries of the theory. So one of the most striking properties of the standard model is its Gauge group, which are the symmetries that you can see, for example, clearly in the Lagrangian explicitly. And together on top of that, the symmetries which govern the interactions and the particle content, we have the electroweak symmetry breaking mechanism, which is driven by the Higgs boson, the only scalar particle in the standard model. So this is important because it takes the whole symmetry of the theory at very high scales and through a process of spontaneous symmetry breaking, breaks it down to the symmetries that we see, which are the electromagnetism and color and the strong force associated symmetry. And this is a mechanism where you have a scalar particle and vacuum energy, as some of you probably have already heard about. So what about the standard model of cosmology? Well, this is interesting to talk about because the particle physics world is based on giving exact, precise descriptions and a lot of certainty about the things that we have found. But the interesting thing about the standard model of cosmology is that it's a framework of ideas that describes surprisingly well what we can observe. And there are still a lot of things like what is the standard model of cosmology is somewhat of an open question. What things are included into it within the ideas that we have, but this is more or less the picture. So we have a universe that is made out of dark energy, dark matter, and matter. The model in itself doesn't explain what dark matter is, and dark energy is just a form of vacuum energy with negative pressure. But this, at first sight, kind of simple thing allows us to trace the kind of history of, the whole universe, and it's in agreement with what we can see and what we have measured, which is a lot. What we have actually measured is, I get surprised every time I think about the fact that we have things like the CMB and we can measure things like that. So just take you through the history of the universe very quickly. The first thing we start with is the cosmological principle, which is just saying that the universe is homogeneous and isotropic. It's more or less made out of the same stuff, and we look around and it looks the same. Then we have some kind of event where suddenly you have an expanding space-time that pops up, and a period of super fast expansion that people call inflation. The specific mechanism of how this happens is not necessarily included, and sometimes not even inflation is included in what we call the standard model of cosmology. But there's a lot of other interesting observations that we do about the universe that can be resolved by thinking about a period of this type of expansion. The models that drive that are typically based on scalar particles that through the potential energy drive this kind of expansion for a while until it stops. And then the scalar drops its energy back into the universe reheats. And these kind of quantum fluctuations of this field that drove inflation are the seeds that, even though the universe is isotropic and homogeneous, they are the seeds that create all of the kind of features that we actually see, even though in a large scale it's isotropic and homogeneous. At some point, when these perturbations propagate in this hot universe, atoms start forming, and while things start expanding, they start cooling down, and at some point, all the photons that are in this soup, in this hot plasma, stop interacting so strongly or coupling so strongly to everything else, and they're actually managed to travel freely, and that's what we measure as a CMB, because this is light that suddenly was able to travel. It was everywhere, and it's been stretched out for a long time until we measure it today. And from the specific details that we have measured to a great precision, we can understand certain aspects of our universe. Then once this happens, the light is being free and traveling, dark matter starts to collapse gravitationally, because even though as far as we know, it doesn't interact with anything else but gravity, or at least not strongly, it does with gravity. So it starts collapsing, and then baryonic matter, which is what we are made of, start also assembling with dark matter through gravitational forces. Then a big cosmic web of dark matter forms, and then at the end, things have expanded enough. We have the negative pressure, which people call the cosmological constant sometimes, that drives this accelerated expansion that we've measured. Okay, right, so that's what we know. So what is it that we don't know? So the standard model doesn't have, as you probably heard in talks in this conference, it doesn't have a candidate for dark matter. There's this very big important part of what we call the standard model of cosmology that is not in the standard model. There's no inflation, no mechanism explaining inflation, even though you could do it with extra fields. They are not in the standard model, even though the whole idea of inflation in itself is still something that is very interesting to think about and discuss. It's not necessarily something that we are, let's say, everything points to the fact that this is a very reasonable idea, and I think that as well. But at the same time, there's still some work to do before we can have conclusive tests that it actually is the way we think it is. And this is I could talk for an hour about this. But another thing that comes up from the standard model is that if you try to calculate what is the vacuum energy of the universe, if you try to do that almost an academic exercise within a quantum field theory, the prediction that you come up with is naturally or naively huge, much more than the vacuum energy that is predicted by the standard model of cosmology. And this is kind of a disagreement that is based also on the fact that there are fundamentally very different theoretical frameworks. So we see a lot of matter and not a lot of antimatter. The standard model has no explanation for that. It has some small mechanisms to generate a little bit of that asymmetry, but definitely not even close to what we observe. As I was kind of hinting before, the origin of all these quirky parameters, why does it look like that? Why do you have such a different mass spectrum, even though everything looks kind of like 3 copies of something? There's no gravity included. Why is the Higgs so light? I mean, these are all open questions that some of them are connected with what you think is elegant or beauty in the theory and might just be answered, well, just happens to be one parameter that is fixed on the part per 10 to the whatever, and that's fine. And if you feel comfortable with that, that's a way of thinking. But so far in physics, when you get driven by the principle of maybe this has a more elegant explanation, you get somewhere. And then it's the fact that in the standard model, as we were going to discuss a little bit more later, the vacuum is unstable. So in the standard model of cosmology, we've already touched some of that. But for example, this cosmological constant, this vacuum energy that creates negative pressure, is it constant? We actually don't know. So as far as we know, it kind of looks like it, but it is an interesting question to try to explore what if it's not. There was a problem about missing baryons that apparently was solved this year by finding some strings within galaxies filled with baryonic matter that might account for that kind of. This is not the same problem as the baryon-antibaryon asymmetry, but it was a problem for a while. There's different measurements of the Hubble constant that don't agree with each other. It's unclear whether this is a systematic error of the experiments or if there's something behind that. And some people think that just having a model with 6 parameters is too much, and we should find something more elegant, the same kind of argument with the unification of the forces. As you can see, all of these things are related. So even though they're in structure very different models, they do have some connection. For example, we know that we can explain inflation with a scalar particle. We know that dark matter maybe could be a particle, though there's very interesting ideas flying around and being renewed in the literature about thinking of dark matter as microscopic black holes, something that people have kind of given up on, but it's resurging because there's been some interesting developments that make it again a very sensible idea. So might be a particle, which is definitely a very sensible idea, but it might not. But there's another connection there. There might be some other connections between how do you generate the vacuum of the theory and how do you generate the matter and antimatter asymmetries through something we were going to talk a little bit about, which is vacuum decay. And there's this super big question of how do you connect the gravity of it all. So these are some of the connections that are within both of them. But as I said, this leads to many ideas of how to go beyond these standard models and justifies why it makes sense to think about these ideas. And there is no lack of ideas of things that might be beyond the standard models. What we lack is some way to apply the scientific method and go and have experimental measurements and being able to test all these ideas conclusively, all these predictions from these theories. From the particle world, we can add extra symmetries on top of that gauge group that we had in the standard model, unify all the forces, which comes with extra particles that we can search and have been searching for in colliders, like things like supersymmetry. There's many different models, just based on the fact that we are kind of waiting or thinking about ways of measuring and finding, like with new accelerators and new experiments, ways of kind of weeding out which ones of these make sense. They all typically have a dark matter candidate, have things like that, like grand unification models, like I mentioned as well, come with that. And then dark matter candidates that might be just an extra particle you add to the standard model, or some particle that comes from grand unification scenarios used as a consequence of this extra symmetry that unifies the forces. And there's ideas as elegant as you want them and as phenomenological as you want them are there. In cosmology, there's people that say even, well, what if GR is not the theory of gravity at large scales? This is people that think about modified Newtonian dynamics. As I mentioned, black holes as dark matter could be an answer to these. There's many inflationary models, which in itself is kind of one of the biggest questions in inflation. Like, yeah, there might be something like inflation, but there's so many models and they depend on initial conditions that are sensitive to quantum gravity. So what are you saying? Because you don't really understand the initial conditions, what are you going to predict? And this is a very lively, very interesting field of research that I think about. And there's a lot of potential for new discoveries here. And the same, like thinking of grand unification of forces. The truth is that all of these things, all of these open questions from both sides, a repeating theme in all of them is the vacuum and scalar particles. Inflation can be driven by a scalar. You have vacuum decay. You have dark matter could be a scalar particle as well, could also be a fermion, but all grand unified theories that add extra symmetries also come with the consequence of more scalars that then you can search for. So my argument is that there is a very interesting thing that connects a lot of these aspects and a lot of these open questions, and that at the same time, we are precisely in the moment of being able that for the first time, testing these things experimentally, as I will tell you. But before that, I have to tell you a little bit about what is vacuum decay. I'm gonna go very quickly through these. So feel free, this is very interesting ideas. Feel free to ask me about it later on, because I'm gonna fly through this, but very quickly. It turns out that in a quantum field theory, you have something analogous to what you call the potential energy in mechanics. It's a little bit more complicated because we're talking about fields, but a lot of the intuition remains the same. So as you know, probably in the standard model, you have the potential of the Higgs that they call the Mexican hat potential. And what you have the process of symmetry breaking is how did the Higgs get from here, to down here. Now, the truth is that in general theories that are not necessarily the standard model, that are beyond the standard model, this potential might look very different. It might look something like that. So why do we say that we are in the minimum of the potential? This is because what we have is an action for let's say a very simple theory of just one scalar field, an action that we minimize through the principle of minimal action. And the configurations that minimize this action here turn out to be, if you think of scalars that are constant, that they don't change in space, the things that extremize this action end up being the things that minimize this potential V here. However, and this is the interesting part, the actual energy of the system is not just this potential energy. That's true only for fields that do not depend on space. If the fields depend in space, the energy that you're minimizing is this functional here that depends both on space and on the potential energy. So you could have some weird field configuration. Remember that a field is something that just gives you a value or an operator for every point in spacetime. So you can have a configuration in spacetime of this field that extremizes that action that is not necessarily constant. And those configurations, actually, what they can represent is just quantum tunneling, like in your typical quantum physics course. You are writing a theory in this minimum, and it turns out that there is a configuration through which a physical process of quantum tunneling can happen, and you can decay, and your theory can decay to a deeper laying minimum. This is super interesting because, as you probably know as well, a minimum is associated with the physics. So in the standard model, the minimum of the standard model is that what gives you how the symmetries of the theory are broken, and it gives you, for example, the gauge boson masses, like in the standard model, and the W boson masses, and which symmetries are respected. And the physics here might be who knows what. So this is very interesting to think about, and we know how to calculate the transition probability, the decay width of this type of processes, and it's something that can be used to test new theories because we know we are here. We know in which minimum we are. So if you have a theory that predicts that instead of staying in the one that you want, you decay to this one, that theory is just not okay. Right, so that's vacuum decay. So what happens when that process triggers? Well, what happens is that you have a bubble that pops up, that inside of that bubble, which is the field configuration, this scalar field that is just permeating the whole space-time, suddenly one of these non-constant in space configurations pops up, which is a bubble that has this true vacuum inside with physics that we don't know what it is. It depends on the theory, that starts expanding at the speed of light. And then expands super fast and starts doing, wreaking havoc in the universe. And this is very interesting for many reasons. You can use it, for example, to explain the baryon-antibaryon asymmetry. Under certain conditions and in specific models, you can make it so that this bubble expanding, the true vacuum that is inside is where we are now, so the vacuum that we want. And then this bubble expanding starts sweeping away antimatter with the walls. The walls start sweeping away antimatter and then generate the symmetry that we have. This is a very schematic explanation of a very complex physical scenario, but that is also very interesting. But those bubbles also, as you can imagine, disturb spacetime in a big time. So they're very interesting. So it's important to know when these transitions happen. When do these bubbles appear? When can you have this kind of quantum tunneling process? Because it could happen very well, so that when you introduce the concept of temperature dependence, things look a little bit different. So you know that at very, very high temperatures, when the universe was a hot plasma, the potential energy looks something like that. You only have, that your scalar field can only have a value of 0 and is very symmetric. When temperature starts going down, then this potential starts getting a little bit different, and at some point it's going to develop a minimum, which is where you want to transition. At a certain temperature, let's call it a critical temperature. What can happen, though, is two different things. Either...
Sorry to interrupt you. I don't think we can see quite what you're doing right now.
You don't see my screen?
We see the true vacuum.
No, I'm seeing everything. So probably a problem with
I'm also seeing everything.
Okay, maybe it's just okay.
All right. Maybe it's taking a while to update for you. Hopefully you'll catch up. So I'll try to be mindful to maybe don't rely super much on the drawings that I'm doing, but essentially what can happen, though, it's a different scenario. I'm going to write one scenario on the right and one on the left, that the actual shape of the potential is such that it can be like that, like a smooth kind of thing, where then the field can roll down smoothly, and that's what's called a second order phase transition. Or what you can have instead is that when temperature goes down, this actually turns out in something like that, where you have a wall and where you cannot roll down classically. I'm using intuition borrowed from classical mechanics that turns out works very well here, but that's for other reasons. But you have a wall here that then allows you to create that tunneling and creating those bubbles. And those bubbles that can explain baryon-antibaryon asymmetry. So it's interesting to see when that can happen. And that gives you the necessary conditions for generating this baryon asymmetry, which we understand, and there's just three conditions. You need baryon number violation, charge and charge parity violation, and departure from thermal equilibrium. And all of these three conditions are satisfied if you have one of these bubbles just wreaking havoc in space-time. So turns out that, before we go there, turns out that in the standard model, this is the case. So in the standard model, when the temperature is very high, the potential is kind of like a U, and then when the temperature goes down, you have that Mexican hat potential, but it happens in such a way that you don't have a bubble. And we know that such a bubble would explain a lot of the holes of the standard model, like the baryon and antibaryon asymmetry. So that's also another kind of pointer towards that. In fact, the standard model is a little bit more crazy than that, because when you extrapolate the standard model to very high energies, what you have is that the potential actually looks something like that. Even though when you go from high temperatures and you want to get to the minimum that we have, you don't have a first order phase transition. When you go to very high energies, to very high field values, the potential also becomes unbounded from below. So there's another process of quantum tunneling where you tunnel to this very high field value that it leads you to a minimum that, in the Planck scale, you don't even know what's going on. We don't even understand what's going on. And the standard model says that this is how it is, if we would believe the standard model. That's just not enough to throw it away, because it also tells us that the lifetime of this minimum here is way larger than the age of the universe. So it could be that we are in this very dangerous place, just waiting until the universe is old enough for the Higgs to tunnel and kill us all. So it's kind of there. It's not such a strong argument against the standard model. But so now that we have understood these key concepts, or I hope at least I've given you some flavor of the ideas in this very short time. The question is, can we measure that? I mean, I'm talking about these big bubbles that expand and do crazy things in space-time, expanding the speed of light. Each minimum is a different universe with different physics. It seems kind of like a little bit of theorists gone crazy and forgetting about experiments. But the truth is that even though you could have argued that it was that way for a long time, we can start, and we are very close from starting to measure the consequences of such things. And I'm going to tell you how. For that, I have to introduce you to two ideas very quickly. One is what people are calling now the standard model effective field theory. This is an old way of looking things that is very powerful. Effective field theories, I mean, that was already used by Fermi to understand, for example, beta decay. But it turns out that if you are at a certain energy regime where you have a bunch of extra physics that is very heavy in much higher energies, turns out, which it makes sense, that the physics that you can measure does not depend on that very high energetic particles that you cannot even produce because you don't have enough energy. So in particular, beta decay was understood as a four-fermion interaction, even though in truth, when we go to higher energies, we understand that what was happening in this little dot here is that we had a W boson exchange. Now, I'm just flying through these things, but this is very interesting. The question that we can ask ourselves is like, well, this here is the standard model, but what if we go another level and the standard model is already a kind of effective field theory, in the sense that you have things in the standard model that actually come from some extra particles in a beyond standard model theory that are so heavy that we just quote unquote don't see them. And this is what leads to the standard model effective field theory formalism, where you just write the Lagrangian of the standard model plus all possible combinations of fields that respect the symmetries of the theory, and that we put some coefficients in front of them that we call Wilson coefficients, and they parameterize any kind of new physics. So given a beyond standard model of particle physics model that have many particles and many symmetries that are very heavy, you can always calculate what are the numerical values of all of these numbers here. The upshot of this is that we can also test experimentally for these numbers. And then we can put limits on those numbers and then understand what kind of theories predict what values for those numbers. And the other thing I want to explain to you is gravitational waves. Very quickly, you take GR, which is governed by Einstein equations, which tell you, well, on one side you have geometry and the other one you have energy and momentum. And let's say you take the space-time, perturb it a little bit with a small perturbation in the metric, which is what tells you how space-time looks like. If you have a certain mass configuration or something, it creates curvature, and that's described by that. And you have a small perturbation of that, and then you plug that back into the equations and do a little bit of carpentry there. You end up having an equation for that perturbation that is just a wave equation that we all know and love. And those are gravitational waves. This is the way that I understood gravitational waves, more than, like fluctuations of space-time. That's a bit out there. And it's what they are. But for me, it was easier as a physicist to say, yeah, you see, the wave equation pops up. Great, now I know what they are. Okay, you being interested in physics, I hope, have probably heard about this whole gravitational wave astronomy business. And this has been fascinating. So we already have measurements of gravitational waves. They actually exist. And we have the LIGO and Virgo interferometers here on Earth that is just, very big arms. And we measure to a ridiculous level of precision their length, and then we can check and check with both of them whether we have some kind of shrinking or moving of these relative lengths and that describes the gravitational wave. And then this is amazing. But we have upcoming experiments with the LISA space antenna, which are just 3 satellites that are going to be arranged in a triangle, and they're going to have cubes of very heavy cubes in them that then reflect lasers between them and create a sort of like immense interferometer outside from disturbances and all the noise that we have on Earth. And we have the Athena telescope, which is an X-ray telescope that they're going to use together to typically probe the things they talk about, which is merging black holes and things like that are very popular because it's the first kind of low-hanging fruit that is incredibly interesting. However, what's also true is that this LISA experiment is just not going to measure specific events. It's also going to measure the stochastic noise, the background gravitational wave spectrum. And this is super interesting in the same way that the CMB was interesting. So you have some microwave antenna that was more like a microphone than a telescope that was measuring this background noise. And it turns out a lot of what we know about cosmology comes from that background noise. However, to measure it to the level of precision we needed, we had to measure it with satellites, for example, the Planck satellite. So we needed to get away from the noise of the Earth and try to measure that background. In the same way, the LISA interferometer, the space antenna, is going to be able to measure that. And what's incredibly fascinating is that these bubbles that I told you about that expand, if a first order phase transition happened in the early universe, and if that first order phase transition is in the electroweak TeV scale, meaning that it's compatible with the idea of this standard model symmetry breaking that takes us to the minimum that we are, this electroweak symmetry breaking minimum, that is precisely within the frequency range of this satellite. So we're going to be able to check whether a first order phase transition happened under certain conditions and certain scenarios. It's more going to be a game of like, if we see it and we find something, I guess I'm out of time, but I'm almost done. I hope I can take an extra minute. So it turns out that if we see it, we are going to be sure we saw it. It might be that we miss it, but we have for the first time ever a chance that we can see data that we can confirm, and we can do the calculations to compare it and check, wow, this is the background consistent with first order phase transition. How does that work? Well, you start with a particle physics model and you calculate some parameters, then you get the spectrum, you have the sensitivity of the experiment. A typical, this is, to me, it's like very striking that we can start doing this. We can actually, we today have the capabilities of starting from a particle physics model, calculate the background gravitational wave power spectrum consistent with a phase transition, and that turns out to be in the sensitivity of this telescope that we're going to launch. It's going to launch in a while. It's 2034, but that's not that long. That's probably when you are going to be deep into research, all of you. And myself, hopefully. As a quick example, the last thing I want to show before I tell you the open questions, the things that are cool to think about in my last slide. This is just an example of what I'm saying with words right now, which is on the left here, we have just a plot where the X and Y axis are some of these coefficients in the standard model effective field theory that I was talking about. This region here that is shaded here is the region of the values of those parameters that are consistent with all the data we have from collider physics, which is a lot, and that the values that are allowed, that if there will be some beyond standard model theory that leads to those extra terms in the Lagrangian, it would still agree with all the experimental values that we have for everything. But it's not only that, it's also the region that through those extra conditions to the standard model Lagrangian change the shape of the potential in such a way that now you can have a first order phase transition, and then you would have a mechanism for explaining, for example, the baryon asymmetry, and you would have this electroweak symmetry breaking happening through quantum tunneling. So this is precisely that region of parameter space is the one that we're going to be able to probe in LISA and similar experiments in the future, because as you can see here, we have just an example. This is the gravitational wave power spectrum predicted by some BSM theory, and up here is the sensitivity of LISA. So there's a little bit of an overlap precisely on the peak. And if you believe the experts trying to do this right now, which I do, this is super exciting and going to be enough to try to test this conclusively in some scenarios. This is super exciting. I don't want to overplay it, but I don't want to underplay it either. We are actually looking at things that happened way before the CMB, because I forgot to mention that, even though the light had to wait until it could travel freely, gravitational waves were just all over the place since the beginning. And we were looking back at, just after the Big Bang and trying to understand whether our universe quantum tunneled or not, with 3 satellites in a triangle flying around. It's fascinating. However, it's very early days, so we have some open questions, and these are things that I think about. Some of them, other things are things that other people think about, but that are very interesting. So, all of these transitions, phase transitions and stuff, they have temperature corrections. You can include coupling to gravity, coupling to a curved background, and all of those calculations are really hard. In particular, there's still a lively discussion about, like, for example, renormalization schemes and gauge dependence and the validity of the approximations that people do to do these calculations. It's really hard to do it in curved backgrounds. There's still like a lot of numerical approaches and intuition ideas that are baked into it that people still need to prove and work more formally. People are still using just simulations to fit possible expressions for this spectrum, which are right, but are not precise enough to take the full potential of this experimental data that we're going to get. And so far, we've only looked at what happens when these bubbles collide with each other. Single bubbles might produce gravitational waves through quantum correction, so we don't even know how to calculate yet. So this is early days, a lot to figure out, a lot for you to get interested in and start being the person that figures this out. And I leave you with my last slide, which is a very interesting document that I would suggest you read, which came out recently in October last year about the roadmap for the future. And it just struck me, just a sentence here, that it's for the first time that we can address these structural questions that are as old as civilization itself. And that is fascinating that we have reached the maturity and developed the technologies to address them. This is happening now and in the following, probably forever, right? But we're starting to do this right now, and this is super exciting. So yeah, that's my talk. Thank you.
Thank you so much, Dr. Camargo, for such an insightful talk. I think we can all agree this is very fresh research on the frontier of particle physics. Now for questions. Our first question is from Oishi Banerjee. Sorry about pronunciation. Will the LISA and Athena experiments perhaps also reveal why the initial phase transmissions of the universe resulted in more matter than antimatter?
Yeah, so absolutely, in a non so direct way, in the sense that one of the mechanisms that might be able to explain that matter and antimatter asymmetry relays on such a transition with bubbles having happened. The question of whether that happened or not, it's still open. I mean, I do believe it happened. It makes a lot of sense, but we don't have this data. So let's say the Athena plays a secondary role here, because Athena, the X-rays are used mostly to pinpoint if you have a particular one thing that happened, like 2 black holes merging, or a certain like population of black holes and the jets that come out. But the center of this would be the ELISA interferometer that then measures the noise. And that noise that comes from everywhere is going to tell us, or it might tell us conclusively, look, we had one of these transitions. And not only that we had them, but it would give us a window to the properties and exact of certain parameters that tell us how did it happen. And if those conditions agree with the conditions that you need for the mechanism where the bubbles sweep antimatter away, then there you go. There's an explanation. And then there will be probably a couple of years of people writing models about how they're writing papers about how their models explain it exactly that way. But that's the way it goes until we get enough data to conclusively say this is the model that predicts exactly that data. And part of that work is going to be trying to understand in that curve that I showed a little bit more of the details of how to calculate that power spectrum, and given a theory, how does that power spectrum would look like. And these are things that, as it happens in particle physics, the same was with the development of the LHC and the calculations needed to discover the Higgs boson. This was going at the same time. Like, people were building the LHC, and still there was a lot of open questions about the calculations you needed to do to be able to take the maximum advantage of the experimental results. Some of it was done in the 70s, 80s, but some of it wasn't. And the same is true here. So it is a lot of potential. What I can tell you for sure is that we're going to be able to check, and we might get some conclusive proof that there was a first order phase transition, in which case there was this bubble, and in which case the mechanisms that explain baryon matter-antimatter asymmetry through this mechanism might be the answer. Yeah, I hope that's a good answer.
Great. Our second question by Anch is, if the LISA experiment doesn't find any evidence of a phase transition, will that be conclusive result ruling it out?
No, and this is the very difficult question that we have to sometimes try to answer as physicists, and it's a really difficult question to answer to people giving us money to do things, which is that it's really hard to prove a negative, right? Like it's very difficult to build an experiment that can give you total certainty that something is not there. Whether what we do typically is like we can build an experiment that within certain kind of, I don't want to call it a guess, but our educated guess of where it makes sense to look, we might find conclusive proof that there is something there. And that's, the Higgs boson. They tried to search for it at LEP, and the question might be the same: was, do you conclusively prove there was no Higgs boson? And the answer was no, we just need to build a bigger accelerator. And now with the LHC and supersymmetry, yeah, we have to update our priors and understand that, okay, maybe what makes sense to look at is something else given the experiments that we have, but it's not that we think that the LHC conclusively proved that there was no supersymmetry. It's very difficult to prove a negative. But you're right in the sense that it might happen that LISA is not enough, but these are relatively inexpensive in a kind of like global level experiments that are giving us an insight never before even imagined. It's just 3 small satellites. It costs a lot of money for a person, but they're sensible experiments if what they want is to answer the structural questions about why we are here,
Another question is by Marley. Could you talk more about the missing baryon problem you mentioned earlier and how it has maybe been resolved?
Yeah, so there was this thing that if you would take at face value the lambda CDM model or the standard model of cosmology, and you would calculate the abundances of certain things or certain elements, you found that what you measured was not enough. Like what we saw with just telescopes and things wasn't enough. There was some baryon matter missing. I found out there was a possible answer while preparing this talk because it happened last year. But what I could understand by reading the paper very quickly was that they found some strings of baryonic matter hidden in certain places within galaxies or between galaxies, that they found some new method of using telescopes to actually measure because it was very faint. And they managed to find these kind of strings of baryonic matter that when you include them into the estimation, they then seem to agree with the prediction from the standard model of cosmology. The details of this, I'm not an expert on. This is just something interesting to mention. I'm happy to read more about it and answer your questions if you wanna ask more about it in the Slack. I haven't delved really deep into it, but it seems like it's been resolved. This is not the same problem as the baryon anti-baryon asymmetry. This is not explaining why there's more matter than antimatter. It's just there was a prediction from the standard model of cosmology that didn't really fit with what we saw, and then now it does.
Great. Another question from Bill Gesu is, what may be the implications of the confirmation of the first order phase transition and the formation of bubbles in the early universe for theories regarding the future and end of the universe?
Theories regarding the what, sorry?
Theories regarding the future and end of the universe.
So what we might learn about it has a bit more to do about what was there before. The truth is that in some ways it might give you some idea about what type of like grand unified theories might be behind the standard model that we all know and love, and how those symmetries were broken, and give us some ideas about in what minimum we are. So in a kind of roundabout way, right now, if you believe the Standard Model, which is the best theory that we have, the Standard Model is saying that ultimately, if we wait long enough, the probability of decaying to that kind of minimum really far away at the Planck scale might be close to 1, and the whole universe might just, disappear in the fire of one of these bubbles. Now, if we manage to see with this that the Standard Model is not complete and that we have a different kind of vacuum structure or a different potential, it might just be that then we make ourselves safer, because then most of these extensions of the Standard Model, the minute you add an extra scalar or an extra fermion to the Standard Model, that kind of curve that went down forever flips up, because that has to do with how the Higgs interacts with itself, which, by the way, it's an argument that I wanted to make, that one of the most interesting things to study together, not only from telescopes and gravitational waves, but also from accelerator physics, is how the Higgs boson interacts with itself, because these are exactly the same parameters that come into the potential energy that, as you see, is fundamental for understanding these kind of phase transition things. So to answer your question, I would have to think if there's something else, but to me what it might tell us is that this thing that the Standard Model is saying, that our universe is unstable, it might prove that it's not, that our universe is fine and stable and perfectly fine.
Okay, we now have another question from Lorenzo.
Yes, so I was wondering, we mentioned that vacuum decay may already have happened once. What are the chances that it happens in the current universe? And if it does, is it possible at all to forecast in any way what are the possible results it can have, like possible consequences it can have?
Yeah, so the truth is that we know it hasn't happened. That's good. We know that the Standard Model says it's possible, but the probability is very low because the universe is too young. So the decay, the lifetime is longer than the life of the universe. And then you can speculate, and you certainly can build beyond Standard Model theories that have a crazy potential where there's another minimum very close, and that the lifetime is close to the current age of the universe. But the thing is that we don't have any kind of indication that that's the case in terms of new particles or particles in the energy scales that would mean something like that. The opposite is very interesting, and this is a big part of my research as well. When you actually have some theories that maybe tell you what dark matter is and solve the baryon-antibaryon asymmetry, and they have neutrino masses, and they're incredible theories. But when you go and do these calculations, complicated calculations about vacuum decay, it turns out that the theories predict that we would have decayed to a crazy other minimum. It would have predicted that we would have already gone through such a process again and not be here in the way that we are here. And that's a very powerful tool to exclude at least regions of the parameters of certain theories using the very powerful experimental fact that we are here, right? But yeah, I mean, you could build easily a BSM theory that evades. I will have to think about. The LHC is making it harder, but I think you can still build a relatively reasonable theory that would have a deeper minimum very close by and might give you yeah, we could do that. But there's no conclusive experimental indication that that's the case.
Right, thank you so much.
Now for our final question from Maria. It's really a two-part question. How confident are you that LISA could reveal quantum fluctuations of space-time that would imply the granularity of space-time itself? And do you think that quantum gravity theories could be put into a test?
That's a really good question. Is it in the chat? Can I read it?
Yes, I think it should.
I don't know how to access the chat here. I'm going to stop here because then I know where it is. There you go. Right. I don't know. This is very interesting, and about the second one, the quantum gravity theories, I'm very unsure. I would say probably not a lot. We could learn not a lot from LISA, this is really far from from my expertise. So I wouldn't be sure. I'm happy to think about it a bit more, but my intuition would say that there's not a lot that is going to be revealed about this with Lisa, because we're going to understand what happened. No, I'm not just going to speculate here. I'm going to think about it. Maybe if you can paste your question again in the Slack, I can go and sit about it and read a couple papers, but I just don't know.
Great. Okay. If you do have any more questions, I'm right now. I'm going to make a channel in Slack for any questions you have for Dr. Carmargo. Thank you so much for being here today and sharing your enthusiasm for the subject. It was truly inspiring. A really great talk.
Thank you.
We will now take a 20-minute break. Our next talk will be by Dr. William Barter on examining nature by testing flavor. That will be at 3:10, so we have about a 20-minute break. And yes, thank you once again.
Thank you. It was nice talking about having people wanting to listen about the stuff that I think about. So that's great. All right.
Thank you. Okay, see everyone in 20 minutes.